So now that we have all the math out of the way and we have the understanding of what Ohm's law is, now we're going to take it and we're going to actually apply it and use it in a circuit. So what we're going to start out with is the very basic single resistor circuit. So we're going to start off down here. We've got a power supply and we have our single resistor. So we've got V1 and we have R1. Now when we designate these, the V1, R1, this is saying voltage supply number 1. V stands for voltage. R stands for resistance, and when we put a subscript down here, that's going to be designating which one that we're after. So V1, R1. So we're going to go in and we're going to say this thing has 12 volts of voltage applied to this, and we have a resistance that's over here at 100 ohms. So now if we go back and we remember what we have for Ohm's law. So what we want to look at is our formulas to start with. So if we remember our circle for Ohm's law, we have voltage on the top, and then on the bottom we have current and we have resistance. We also have Watt's law that deals specifically with power. We have power on the top, current on the bottom, voltage on the bottom. So if we can remember these two wheels, these gives us all the formulas we need to be able to solve for things. So now when we start to apply them, we now hook up a circuit. So a circuit is a set of components that are connected together. We have some sort of a voltage supply, a battery, or if we're in the lab using the voltage supply itself, and we have a resistor attached to this. So now what we can do is we can find which way our current is going to flow and how much we have current flowing. So what we're going to do is we're also going to look at different ways to track how the current flows. Now there are two methods of current flow that we can talk about. The first one we're going to talk about is called electron flow. So electron current flow. So electron current flow, this is where we characterize the current that is flowing from our source through our components back into the source. And when we look at this, we're looking at the path the electrons are physically taking. So electrons are all negatively charged. So they're going to come and form here on the negative part of our voltage supply, and the electrons are going to move away from the negative and move up this direction. Then when they come in contact with a component, we'll do this with red just so we can see our current. So our current's coming up. When it comes up into here, the negative electrons are going to build up on this side of the resistor, making the bottom part of this resistor inherently negative, which means up here, this is going to be inherently positive because there's less electrons built up on the top of R1 versus the bottom of R1, because that's where the electrons are flowing. Then they're going to exit the resistor, keep going, and eventually they're going to get back until they hit the positive of our voltage source. So the little line down here, remember, is negative. The large line over here is positive. So that is electron current flow. The one that we're going to use primarily is the exact same thing. We're just using a slightly different approach, slightly different point of view. What we're going to use is called conventional current flow. So what conventional current flow is, this makes it a little bit easier to track, again, a different perspective. But what happens with this is we're tracking the current flowing from the positive as it goes through the circuit. Electron current flow is when we track from the negative of the supply. So our conventional current flow is going to leave the positive. It's going to come this direction. It's going to come down into R1. Now, as the current flows this direction, R1 is going to be inherently more positive than the bottom side of R1 because, again, we have the positive portion of the voltage supply source here. It's pushing the electrons away from the positive sign. Not pushing the electrons. The other way to look at this is the electrons are moving, and then we have holes, spaces that they occupy, and we're moving those holes through it. So sorry, not the electrons, the holes that they're moving. So then on this side we get an inherent positive state because of we're attached to the positive side of the power supply, which means this side is inherently negative compared to the other side. Then the current's going to flow through and go back in until it gets to the negative of the source to neutralize itself. Now, when we look at this, you might be thinking to yourself, why do we have two ways of thinking for the exact same idea? And the answer is just that. It's two ways to think about it. We're either going to trace the flow of the electrons themselves, or we're going to trace the holes where the electrons can move into. Either way, it's going to give us the same type of polarity on our devices. We end up with positive on the top here, negative on the bottom here, but depending on which method you're going to use, it just dictates your polarities in the circuit. We're going to be using conventional current flow, meaning our current flows from the positive to the negative every single time. All right, so if we come back and look at our original circuit, so we'll just redraw it, just make it easier so I don't have to erase everything. So we've got R1 sitting here at 100 ohms. We've got the voltage source 1 sitting here at 12 volts. And so what we need to do is we need to figure out how much current do I have in this system, and I need to find out how much power that R1 is dropping, and also find out how much power there is in the circuit, my power total. So again with this, I've got I total, I subscript T standing for I total. V1, this also could be written as V total because there's only one voltage supply. This is supplying all the voltage, so we can look at them at totals. So as we go through and solve for this, the current that is now flowing through R1 and through our current total as well, because our current's going to come up here, go down through R1, back around, and back to the supply. The current in R1 is the same as our current total, because if we remember, in a series circuit, current is the same everywhere. So to find that my values, my current total is going to be equal to the current flowing through resistor 1. And to solve for that, I take either the voltage total divided by my resistance total, or I can take the voltage of R1 divided by the resistance of R1. So either method we can use to solve for this, because in this case there's only one resistor, there's only one current path, so we are looking at all these totals. And in this case, my voltage of R1 is going to be my voltage total, because the voltage that comes into the circuit has to be able to be dropped across the entirety of the circuit. And we have to make sure that we account for all of the voltage using Kirchhoff's voltage laws. Everything in has to be everything out. So when we have to have that out being dropped across R1. R1's the only component. That whole 12 volts is going to drop across R1. So we also have the resistance total is also going to be the same as R1, because again, one resistor in the entire circuit, so that's all there is. The total is the 100. So when I go through and solve for this, the current of R1 is going to be the voltage of R1, which is 12 volts divided by 100 ohms. When I do that calculation, I'm going to get 12 divided by 100 is going to give me 0.120 amps. Now remember, when we're dealing with electronics, we want to put things into engineering notation, which we learned before. So to make this compliant with engineering notation, I have to have 1 to 3 digits out here and a power of 3. So to get that power of 3, I have to move this 1, 2, 3 times. And so what I get, 0.120 amps is equal to 120 times 10 to the negative third amps. Because I moved it to the right 3 spaces, that gives me a negative exponent on my power of 10. That also means my current of R1 is equal to 120 milliamps. And there is the answer for my current. Then, based on my power, I'm going to have a power total that is going to be equal to my voltage total times current total. Because again, we're using the same parts. We're looking for total, so I have to use voltage total and current total. So power total is going to equal 12 volts times my 120 milliamps. So power total is going to be 12 times 0.12 if I'm just plugging it in my calculator. And that gives me 1.44 watts. Sorry. So that's how much power I have in the circuit. Well, then I want to look at and see how much power I have in each individual resistor to know how big of a resistor I have to put in. So in this case, I'm going to look for my power of R1, and that's going to be the voltage of R1 times the current of R1. Now remember, in a single resistive series circuit, that resistor is the only thing that's there. So that's the only thing that's going to be dropping power. So the voltage of R1, we know, because that 12 volts has to be dropped somewhere, gets dropped across R1. So I get the power of R1 is equal to my 12 volts times the current of R1, which we found is that 120 milliamps, which was the same as our total. And so our power for R1 is going to be equal to 1.44 watts as well. And what I should see is my power total should equal the power being dropped across all my components. In this case, it is just R1. So power of R1 equals the power total, because it's the only thing that's in the circuit. And now we can go through and solve any variety of these types of circuits using the same formulas. It doesn't matter what we have. So what we'll look at is, I will scroll down a little bit farther and we'll look at another example. So when I come up here, I have got my base circuit. So there's my voltage source, comes around, and I have a resistor. And it's okay if we've drawn it a little differently. We just want to make sure everything's connected together. R1, V1, and we're going to go with our 12 volts here for voltage 1. And resistor 1, I'm going to increase it to a 1 kilo ohm resistor. So now when I do these same calculations, my current total is going to be the current going through R1, because it's a series circuit, there's only one current path, and my current path comes up from the positive of V1, around through R1, down this line, back across, and back up until we get to the negative of our supply. So again, calculation-wise, we are going to have the voltage of R1 divided by R1's value. That's also the same as my voltage total divided by my resistance total. And my resistance total is only R1. I don't have any other options. So when I go to solve this one, I have my 12 volts divided by 1 kilo ohm. When I go through and plug that into my calculator, I'm going to get, oops, pen dropped away, 0.012 amps, which is also the same as saying I have 12 milliamps. Because again, I got to move that decimal, and to make it a valid number, it has to have 1 to 3 digits of 1 to 9, and so I need to move this 1, 2, 3, because I have to move it in groups of 3, so now I get 12 milliamps, or 12 times 10 to the negative third amps. All right, well, what happens if I was given a power but not a resistance? Okay, well, let's look at that. So if I come in and I have my circuit, and I have some unknown resistor here that I got to solve for. So V1 is sitting here at 12 volts. I've got R1, and we don't know what it is, but I do know what my power is, and we're going to say my power total is equal to 200 milliwatts. So not a lot of power. So we got to figure out what R1's value is. We also need to find out what our current is. So we've got current total and we've got resistance R1, or resistance total, because a single resistor circuit. So if we go through and look, I can solve for current total really easy. I just go back up and use my formulas. So if I have power and voltage, I can solve for current. Here I don't have that, but I can do some conversions to be able to find it. So we'll get back down to here, and we will calculate our value. So my current total, so I total, is going to be equal to my power total divided by my voltage total. So power was 200 milliwatts. My voltage total was 12 volts. So I plug that into my calculator, and I get an answer of 16.667 milliohms, or 16.667 times 10 to the negative third ohms. So to make this problem work, not milliohms, I apologize, I'm solving current. I was wondering why that came out kind of weird. This is milliamps, not ohms, amps, because we are solving for current. Current is measured in amps. So with that, I got 16.667 milliamps of current in this circuit with 12 volt supply and combining with the 200 milliwatts to get together to get that value. So there is my answer for my current. And now that I have current and I have voltage, I can then solve for resistance. So my resistance of R1 is going to be the voltage of R1 divided by the current of R1. Now voltage of R1 is going to drop everything, input, output. So 12 volts has to be split up across everything. The only thing that's there is R1. So I get 12 volts across that. And then my current is 16.667 milliamps. And volts divided by amps is going to give me ohms. So I'm double checking my labels to make sure I'm putting my equations in right. So 12 volts divided by 16.667 milliamps gives me a grand total of 719.985 ohms. Now, mathematically, that is exactly right. When we go to grab these out of the shelf, we want to try to build this as close as we can, and honestly, at this point, I would just plug in, it's approximately equal to a 720 ohm resistor. That's what I would grab to make this work. They're going to fluctuate, that 720 is going to fluctuate a little bit just based on manufacturing costs, but we're going to get in there. And the reason for this again is we want to get into our accuracy. Our accuracy is 3 decimal digits, so that's why we carried out the math to this part of the 9.985, and just understanding that that is only 0.015 ohms different from our standard value of 720 ohms. So there are times where we want exact values when it comes to resistance, but there are times where it's like, this is going to be close enough for what I'm after. And if we think about it, if we go through and we plug in a 720 ohm versus this, we're going to have 0.015 more ohms of resistance, which means my resistance is going to go up ever so slightly, and therefore my current is going to drop ever so slightly. So this might plug it into a little bit closer to like 16.5, 16.4 milliamps, somewhere in that realm if we use just the 720 versus the 719. But either way, no matter how we do it, no matter how we look at this problem, it's really, really easy as long as we have 2 parts of the problem. If we have voltage, current, power, or resistance, as long as there's 2 of them, we can solve the rest of the values. Does not matter.